today. As I think
that's great.
Fortunately, the good day.
A good day. Yes, it's a good day.
This, your lecture, international lecture. So hopefully through this meeting, Ocean Engineering Professional Guest Lecture, we can together more explore about the ocean renewable energy on ocean energy. So your title or topic of this lecture is optimizing the development of technology in renewable energy for response to the challenges of the energy transformation in Indonesia. I think this topic is very famous and sexy topic in several couple of years recently. Yeah? So we in Indonesia especially are struggling for how to understand how to adopt a new technology and develop our technology even in our island region for the sake of the application of the renewable energy system, especially from ocean energy. Yeah. Also in our department, Prof, that in Ocean Engineering Department ITS, especially in the study program of postgraduate, we have like study concentration of study about the ocean energy, the mechanism and how to develop new system, and also application for several locations in Indonesia. And also for our graduate students, also several topics, maybe last couple years already studied about the ocean energy. Yeah, again, we hope also from faculty, we always support effort to develop and to make more understanding and studies about this renewable energy in our department and our faculty. So hopefully this lecture has fruitful advantages for all of us, especially, and for our students, Prof. Okay, I think this our short speech, yeah, for opening this professional guest lecture from Professor Zhiqiang. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, sir, for insightful and inspiring welcome remarks. We truly appreciate your contribution to our event. And now, before we begin, I would like to briefly explain the background of our event. The Professional Guest Lecture is a routine event held by HIMATEKLA ITS, which aims to provide insight regarding the latest maritime issues. This year's Professional Guest Lecture has the theme Optimizing the Development of Technology in Renewable Energy in Response to the Challenges of the Energy Transition in Indonesia. And even though this event is held online, I firmly believe that it will not affect our spirit, and we hope that we are able to serve you with the best experience. Next, I'll be giving you a brief explanation of our rundown for today. So the webinar will be structured as follows. Okay, so first is opening. Second, Professor Zhiqiang will deliver his lecture on renewable energy, which will last for approximately 75 minutes. And after the lecture, we will have a Q&A session where you can ask questions directly to our honorable speaker. Then we will have a brief photo session. And finally, closing. Ladies and gentlemen, we have now come to our main agenda, the insightful presentations and discussion session by our keynote speaker. And to begin, I'd like to firstly invite our moderator for today, Muhammad Shafiq Fadli Rahman, a student of Ocean Engineering Batch 2021, who is now the president of ITS MUN, and to guide us through the discussions and activities. Shafiq, it's a pleasure to have you with us today, and the time is yours.
Thank you very much for our lovely MC, Atira, for the introduction. And it is a wonderful time for me to be here with the honorable lecturers and fellow students from Ocean Engineering Department of Institute Technology, 10 November, Surabaya. Good afternoon to everyone. And since it is quite early in the day in Newcastle, I believe it is around 9:22 a.m. Good morning to our honorable guest lecture speaker for today, Professor Zhiqiang. My name is M. Shafiq Fadli Rahman, or Shafiq in short, and I will be the moderator for our guest lecture. To begin, I would like to firstly do a brief introduction of our lecturer, who will be with us to share his knowledge, research, and thoughts about future ocean renewable energy prospects, challenges, and technology development in Indonesia. Professor Zhiqiang himself is a head of marine, offshore, and subsea technology group and is a Lloyds professor of offshore engineering in Newcastle University. He is a leading researcher with over 200 publications and has international recognition in the field of offshore engineering, with focuses towards offshore renewable energy, hydrodynamics, structural dynamics, basin experiments, Arctic engineering, and more. Simply put, he is an astounding world-class lecturer from Newcastle University, and it is an honor to have you here, Professor Hu. We will have 75 minutes of presentation from Professor Hu, followed by a Q&A session for around 15 minutes. And without further ado, to the Honorable Professor Hu, you may start your lecture now. Thank you very much.
Thank you so much. Shafiq is my pronunciation, right? Yes,
Correct.
Thank you. I would like to share my screen. Let me try. Okay, can you see my screen?
It is visible, Professor.
Okay, thank you. Good afternoon, everyone. My name is Zhiqiang in Newcastle University. And today, I think I will give two presentations in this lecture. Firstly, I will introduce our group, the Marine Offshore Subsea Technology Group in Newcastle University. And this is a brief introduction. And after that, I will give, I think, academic lecture on the floating offshore wind turbine. So first, I will give a short description of our group. Our group, the Marine Offshore and Subsea Technology Group, we have totally 16 academic staff. And we have 4 divisions in our group. I think that's quite similar to those that in ATS. We have marine engineering, we have naval architecture, we have offshore subsea pipeline engineering, and we have shipping and logistics. So although we only have 16 academic staff members, but we cover that, I think most of the prevailing research and teaching aspects in this field. Personally, I'm leading the offshore subsea pipeline engineering division. So you can see that's mine. I think we have 5 staff members in this field. And Dr. Kevin Pazuki is now leading the marine engineering, which is very strong in our group. We have a long research history in marine engineering. And besides, for naval architecture, Dr. Simon Benson that is also leading this division. We have totally 5 staff members in naval architecture research, also related to ship engineering. In addition, 2 of my staff my colleagues, Professor John Mangan, was leading the shipping and logistics. And yes, I think yes, 2 of your colleagues that are studying as a PhD student studying in our group right now, and Professor John Mangan is their supervisors. In our group, we are focusing on the research, I think cutting edge research right now. And there are three aspects in the research right now. The first one is the marine hydrodynamics and structures. Although this is, I think, we think that quite traditional research about they are the fundamentals for some cutting edge research, and for the for example of the renewable energy research, we must build a solid foundation on the hydrodynamics and structures. So we conduct some research on the marine hydrodynamics through CFD simulations. We also do some research on AUV and ROV, and also structure dynamics research. Recently, this direction, there are also some more, I think, latest new research in this direction, such as the hydrogen transportation and CO2 collection and transportation, which are very, I think very new and very important for us for the UK to reach the net zero target in 2050. The second research direction is marine resources and renewable energy. This relates to the offshore renewable energy very much. I think that's also match well with the theme topic of this the lecture that I just read through the PDF form. In the offshore renewable energy fields, we focus on the offshore wind because the UK has a lot of the offshore wind resources, and this is another main contribution that we harvest energy from the ocean. And besides the offshore wind, we're also doing some research on the wave energy converter and some tidal energy converter. The third research aspect is about sustainable shipping and marine engineering. So this is a combination of the marine engineering and the shipping and the logistics, because these two aspects work together very well. In Newcastle, we have a harbor. I think one of the largest harbor in UK. It's called Tyne. We have the river, the Tyne River. So the local industry and Newcastle University are working together to build a clean Tyne shipping corridor, aiming to reduce CO2 emission on the shipping emission, on the shipping and the harbor operations. So on these fields, we have successfully guaranteed several projects collaborating with local industry applied from the EPRC or from EU. So we focus on shipping and ship propulsion. We focus on how to reduce emission reduction in the transportation and try to achieve a clean energy efficiency improvement. So these are the three aspects that our group, the Marine Offshore Subsea Technology Group, is doing well. I hope that we can find some common points between Newcastle and ATS. Secondly, I want to introduce some change in our research. And what I said that in the past, we focus on the traditional hydrodynamics and shipping, for example, the hydrodynamic structures, shipping logistics, something. But now we are changing. We are changing from shipbuilding and offshore oil and gas production to net zero related investigations. And we are also changing that from traditional research methods, for example, from numerical analysis, from experiments, from CFD simulation, to we also include the new technologies, including the artificial intelligence, big data, and digital twins. I list three successful projects here about the recent projects. And you can see that most of them built or proposed based on the application of the latest research methods, including AI, digital twins, etc. So our group, we're trying to catch up with the latest development in this field. Next, I would like to introduce some local industry at Newcastle, because we are collaborating tightly with this local industry. Newcastle is the center of the offshore engineering in England. So there are quite many offshore engineering companies at Newcastle. Now, I think that most of these companies, they are also changing from the oil and gas production to offer renewable energies. So they collaborated with us very well in the past and right now, and I believe in the future as well. So for all this industry, let us introduce, for example, the Baker Hughes and the Technip FMC. These two companies, they are world famous cable manufacturing companies in the world. They are manufacturing flexible cable, which is very, very important in the offshore engineering industry. Now they are also developing the cables for the electric power transmission. We also have some underwater vehicles, AUV and ROV manufacturers such as SMD and Royal HC. SMD was initiated, become by several staff members from Newcastle University. And they are, I think they are world famous in the developing these high technology vehicles in the sea. In the middle of this slide, you can see Catapult, offshore renewable energy Catapult. This company locates at Blythe, at the seaside of Newcastle. It's world famous research institute for offshore renewable energies. It has the most advanced testing facilities for wind turbine blade. And beside here, on the right of the slide, you can see the Dodger Bank wind farm. Dodger Bank is the largest offshore wind farm in the world right now. And Newcastle is one of its supporting bases. So all these local companies, they are working together with our group to develop some latest technology, and they also very kindly to host the technical visits and also some student placements from our group. We also have an industry advisory board. This board, in this board, every year, I think we organize 2 or 3 times for this board meeting, which help us to understand the industry demand and their suggestions to our education. So for summary of this slide, I just want to say that in Newcastle, we have quite a lot of offshore companies in offshore engineering and offshore renewable energy fields, and we are working very well together. In the last slide, I just show some research testing facilities in our group. We have our towing tank. This towing tank is not very large. It's only 37 meters in length, so it's not large, but it's very convenient for students to use. So our UG students, our master students, PhD students, they use this towing tank to conduct their research very well. We have a wind wave carbon tank, and this tank can be used to simulate wind, wave, and current at the same time. So we have conducted quite a lot of experiments for the wind turbine. in this facility. We have a Blythe Marine Station, and in that station, we have two, I think, important research facility. The first one is Emerson Cavitation Tunnel. This cavitation tunnel is used to conduct research on the propeller. It's a unique testing facility among UK universities, because in UK, there's only one. Totally, there are only two cavitation tunnels in UK, but one is for military use. So for civil use, that we only this one. So this very unique research facility in UK. And the other research facility is that we have a research vessel. It's Princess Royal. This vessel is very important for our group. We often conduct quite many full-scale measurement research on board. And we also use this vessel to host some technical visits from the international universities and other guests. Now, our group, the Marine Offshore Technology Group, we are one of the most important groups in the School of Engineering at Newcastle University. So this is the link, website link, for you to understand more about our group. There's a lot of information through this link. So if you're interested, you can just Google it online. In School of Engineering, there are totally 5 disciplines: at civil engineering, mechanical engineering, electrical, EEE, and chemical engineering, and us, the marine technology. So we are working together. We conduct a lot of internal collaborations within the School of Engineering. Okay, thank you. This is my first presentation, short introduction of the Marine Offshore and Subsea Technology Group. And next, I will share my screen for Okay, can you see my screen?
Yes, it is visible, Prof.
Okay, thank you so much. Well, this is, I think, let us talk about some academic information. And I hope that this topic about the floating offshore wind turbine match the theme of the event. Floating offshore wind turbine, I think it's promising in Europe, because the wind resource varies very well. This is the main resource that people here in Europe is harvesting the offshore renewable energy. Well, I understand that there's some difference between the different countries in the world. Different countries have different resources, but I hope that in this presentation, that I can share some not only the specific knowledge, but also the methods that we are doing research to share with you. And if it's possible, I hope that it can benefit you, the research in ITS, and we can find some matching points to start some collaboration in the future about how we develop that offshore renewable energy harvesting system in the future. So the topic of my presentation is a dynamic performance analysis of the floating offshore wind turbines with artificial intelligence technology. So I will give my presentation through the 5 parts. But firstly, I will give a short description on the latest developments of the floating wind turbine. And from the part 2 to 4, I will introduce the method of that I use not I, but my research group are using to conduct the dynamic performance analysis in the recent years and share with the method with you. And finally, I will make a brief conclusion. So firstly, it's about some background information. Offshore wind is developing quickly, not only in UK, not only in Europe, but also all the world. But I think that UK and some European countries are taking the leading position because the offshore wind developed earlier here, and also that for the wind energy resources. Sorry, if you can see that, if you can see my mouse, that this big red square here, this is the Dogger Bank offshore wind farm, and it is the largest one in the world. Currently, only currently, maybe some years later, there'll be more about the offshore wind farm will be built quickly, especially I think in the Asia countries, in Korea and Japan, China. I think there may be some years later be bigger and bigger offshore wind farm will be built. The Dogger Bank offshore wind, you can see that more than 100 kilometers away from the UK coastlines. When its building completed, it will be able to provide 5% of the total current UK demand. It's quite large. It's quite large. And besides UK, there are also some other offshore wind farm development. For example, I give example in Norway. This offshore wind is a floating offshore wind farm. It's called High Wind Tempe, and now it's also under construction. And this floating offshore wind farm will have 8 megawatts floating high wind turbine. And its electricity generated will provide electric support for the 5 offshore platforms when they having the offshore oil and gas production. So they don't need to burn oil and gas on board. They just use the renewable wind energy. For the floating type, and when the water depth is shallow than 50 meters, people would like to use fixed bottom wind turbine because the fixed are easy to operate, easy to get on board. But when the water depth is larger than 50 meters, the mooring system or the foundation structure, the cost of the foundation structure will increase dramatically. Then people would like to use floating type and use mooring system to position the structure. And this is very easily to be understood for through the experience of the offshore engineering, offshore industry. So for floating type offshore wind farm, they think that Norway and UK are taking the leading position because high wind is a smart type offshore wind turbine. It was, I think, firstly proposed and put into commercial testing in around 2011. And after 6 years on full-scale measurements, the first offshore wind farm, commercial floating offshore wind farm, was built in September 2017 in UK, in Scotland. The name of that offshore wind farm is High Wind. And now it's nearly, I think, successfully running for 6 years. So that proves that the high wind, the spar type floating wind turbine is a successful design. The challenge is how to control the cost because expensive installation and operation maintenance is quite expensive. So that's also the aim of the research and the academic fields want to achieve is that some good ways that in the future which can be used to lower the cost of the operation and maintenance. Well, currently there's one commercial floating offshore wind farm in the world, but at the same time, many other practices are also conducting. For example, in Japan also have some mid-scale tests in the last, I think, 10 years. But the commercial, real commercial wind farm developing is still under construction. And these two are spar type supporters. It's very popularly used in deep water, where the water depth is, I think, more than 100 meters. But for those seasides with water depths between 50 meters to 100 meters, spar type is not feasible to be used. And people will use semi-type, these two. The semi-type supporter will be more frequently used. For example, the wind float that in Portugal, and this also in China, it is also a semi-type. This is the first semi-type floating offshore wind turbine in China that operated. It's not far from Hong Kong. It's in Guangdong province in 2021. And in 2022 and 2023 this year, another two semi-type floating offshore wind turbine were also installed and start operating. Okay, so that's just a brief background information. And next, I will introduce about the dynamic performance analysis. I will introduce three methods to conduct the dynamic response analysis. The first method is theoretical analysis. That is a principal method that people use. That's the foundations use aerodynamics, hydrodynamics, all these multiple disciplinary to conduct analysis. This is the foundation method. And the second method is model experiments, model testing. This method is used in the offshore oil and gas industry frequently, very popular. And they also can be used to conduct the analysis for the floating wind turbine. And third method I will introduce is the AI technology, how the AI can help us to conduct more feasible and more accurate prediction and analysis. So first, let us go to theoretical analysis. So for the dynamic performance analysis of the floating wind turbine, it is very important and very crucial because floating offshore wind turbine is a nonlinear, rigid, flexible structure. It's very complicated system. The load applied on this system is very complicated. For example, there's an aerodynamic loads, that's wind blow on the rotor. So the aerodynamic loads is important. Hydrodynamic loads, as wave loads on the supporting structures. The mooring system has also some dynamic load applied on the system. And the operating load, that's due to the rotating of the rotor. This will also induce the load, the gravitation loads and some other loads such as marine growth, the ice, and sometimes even earthquake, tidal loads. So all these loads, they might applying on the floating wind turbine system at the same time. So when we want to analyze and when we want to understand the dynamic performance of the system, we must firstly know how to calculate the load applied on the system. So this is the first step we must we must do. When we conduct this step, we will know how to calculate the wind load. For example, the aerodynamic loads. We use aerodynamic series to calculate the wind loads. The method itself is not a new one. It's the bladed element momentum theory. It's old. I think it's the old theory, but with some corrections, it can still work very well to do the prediction, to calculate the wind-induced load on the rotor. Hydrodynamic load, I mean the wave loads on the supporting structures. So linear potential flow theory, I think this is also one of the fundamental theories used in naval architecture and offshore engineering fields. It's also not a new theory, but it can be used conveniently in this field. There are some commercial software that are very popular, such as WAMI, CSAM, or Aqua. They also are very popular and can be used to conduct analysis. Mooring load on structure. Mooring is a very complicated facility, and when we conduct the dynamic performance for the mooring loads, we can use catenary mooring theory and lumped mass methods to consider the quasi-static response and the dynamic response on the mooring system. And the last the loads calculation method is about the servodynamics, which are the operation due to the pitch control of the blades on the wind turbine. It will induce some additional loads on the structure. So here I give examples for the four kind of the loads applied on the system. When we know that how to calculate the loads applied on the system, that is the first step we need to do. And after this step, we need to do the second step, that is to build a model, a mathematical model for the floating offshore wind turbine. Because the floating offshore turbine is a multi-body deflection dynamic system. I do know that for the floating body, we normally assume that the structure is a rigid body. So it has 6-degree motion. But for floating wind turbine, it's a multi-body system. It has 8 degrees of freedom, because the rotor had 1 freedom, and the nacelle can also rotate at heading control. So it has 2 more freedom of motion than the traditional floating offshore structures. So this makes the system more complicated. In addition, it's a combination of a rigid, flexible structure. The supporting platform is a rigid body. The tower of the structure is the elastic structure. It can vibrate. The nacelle is a rigid body, but the 3 blades are flexible structure. Its deflection, it deflects, and the deflection at the tip can be very large. So this makes that system complicated, but we need to build a mathematical model for this system. In this slide, it shows that for a simple semi-type floating wind turbine, this system can be divided into 8 bodies. So B0 is a mooring system, B1 is a platform, B2 is a tower structure, B3 is nacelle, B4 is hub, and 5, 6, 7 are 3 blades. So you can see, even for the most simple floating wind turbine, it can be divided into 8 parts. And each component here are used to calculate the internal load on the system. The internal load means the movement, the bending moment or shear force, and the tension force. All these are used to evaluate the strength or the stress strain of the structure for people to evaluate the safety of the whole system. So this is the second step that we need to do for the theoretical analysis. The first is how to calculate the load. The second is how to build a mathematical model. And the last one, the third, is to find a calculation method. In my research team, we find a method that's called the Keynes dynamic equation. This is a very useful dynamic equation, and it's feasible to build a program. So we use this calculation method to do the calculation to calculate the dynamic performance of the whole system. And with this calculation, we built programs with Fortran language. We use Fortran to carry out the calculation. And we built an in-house program. Its name is Darwin. So this is our in-house program, which can be used to calculate the dynamic performance of the floating wind turbine. And this program uses time domain analysis method. So the meaning of time domain is that at any time moment t, we can use the motion of the system to calculate the loads, the aero loads, hydro loads, mooring loads, operation loads. We make the loads on this system and through the Keynes dynamic equation to calculate the motion at next time step at t plus delta t. And then iterate. Then we can calculate, we can obtain all the dynamic performance for the floating wind turbine in time series. These time series results are very important for the engineers to understand the structure, dynamic performance under the severe state, under the operation, the rated wind speed condition. And these results are very useful for the engineer to reach the optimized design. This optimized design means that the wind turbine can survive in 20 years or 25 service life safely and keep the cost of design and keep the cost of the operation and maintenance as low as possible. So an accurate method to estimate or to predict the dynamic performance of the floating wind turbine is very important, of crucial importance in the offshore wind industry. So this is the first method that is popularly used in the dynamic performance analysis for the floating wind turbine, theoretical analysis method. And next, I would like to introduce the model testing. And when we complete the theoretical calculation, we have the results. We can have the results. But whether it's true, whether it's true that people can rely, can trust, and to do some other design, that's a big question. And the model tests we always use to validate the analysis results. I myself have some experience conducting basin experiments at the deep water offshore basin at Shanghai Jiaotong University. So this is the deep water offshore basin, and this is the experiment when I conducted there. But that's about nearly 9 years ago. So the technology they use at that time, when I conducted experiments, might be old, but those methods still can bring some references for the people who are interested in using the basic experiment technology nowadays. So at that time, I conducted experiments for two types of the wind turbine. The one is spark type and the other is semi-type. So now I only use the results for the spark type to give a brief introduction. When we conduct experiments, the ratio scale is 1:50. That's the high wind. That's the same as that used in Scotland, the high wind spark type. But we use that Unreal 5 megawatt wind turbine on board. When we conduct experiments for the floating wind turbine, there are some challenges. Why I mention this challenge because that to conduct experiments for floating wind turbine, there are some big difference, right? A very important difference between this one and those of the traditional offshore structures. And the most important difference is the first one I show here about a scaling methodology. That's the front number and the Reynolds number must be considered simultaneously. If for them, if any of you that know have some experience of basic experiments, you must know that we normally consider Reynolds number. Front number when we conducting the experiments. We neglect Reynolds number. However, for the floating wind turbine, because wind load is a dominating load and the blades are rotating, so we must consider the effects of Reynolds number. And you know that fundamentally, the front number and Reynolds number cannot be considered at the same time. So this is a big challenge for us. We must consider the effects of both numbers, but fundamentally they can't be considered together. So how to solve this conflict is a big challenge for us when we conducted this experiment. Now, there's a method called hardware in the loop. Hardware in the loop, yeah. This method is popularly used in European countries and to carry out the experiments for the floating wind turbine. Well, but anyway, this method, hardware in the loop, is still a trade-off method. It neglects part of the wind load effect on board. So there's still this problem has not been totally solved. But I hope that in the future we can solve it to find a good solution. So these are the first challenges, and all the others I do not want to see in much detail. When we manufacture the models, we need to control the mass property. We need to simulate the profile of the blades. All these bring a lot of challenge. And one of the challenge is the wind, how to control the wind field in the offshore basin. It's open space, so there's no wind tunnel. So how to control that the wind field to be evenly distributed. So there's on some testing facility and research. And also for the manufacture of the blade of a wind turbine, especially not only the blades very expensive. Have to use the carbon fiber materials to simulate the profile and also control the mass property. And another challenge is how to simulate the towers, the vibration property. Its tower is not a rigid body. it's elastic body, so it can vibrate, and the structure, the one we found can simulate the first mode of its vibration very well. We can't simulate all the other second order or third order vibration mode, but at least we successfully simulate the first order of vibration. That's important because the first order dominates the dynamic performance. Okay, well, the next challenge is about the transducers. And because floating offshore wind turbine, the model is light. Because the model is light, it's quite difficult to arrange the transducer on board, because transducer has some weight. It could influence the whole structure, the property. So there are also some challenge for us when we conduct experiments. And when we manufacture the model, when we complete that, then next is about the test cases definition. So when you conduct experiment, you must consider the wind load, you must consider current speeds, and you must consider the wave, regular wave and irregular wave. So all these cases, combinations, were defined by IEC, and Unreal contribute a lot and give these definitions. So many basins in the world at that time conducted similar testing cases and compare the testing results. So we also conducted these testing cases and we obtained some results. So for example, here, this is a decay test. For decay test, we obtain the damping characters of the system. For the 6-degree motion, we obtain the damping, and we also obtain the mooring property. So you can see here is a comparison between experiments and the Darwin simulation results. So they match very well. And after we calibrate the model, then we do some aerodynamic load, that means the wind loads testing cases. We compare the motions, the pitch motion and surge motion, and also the power export when there's only wind. So basically, you can see that the numerical analysis results by the Darwin program match well with the experiment results. They match well because there's only wind load. But when there's wave included, there's some difference. That, for example, even in regular wave, we can still find that some amplitudes difference and some phase difference, especially when the irregular wave included. The irregular wave bring a lot of change, especially for the low frequency motion characters. For example, here, for the surge motion in this picture, you can see that the experiment date and the Darwin simulation, there's some difference, especially the peak value, although the frequency match well, but the peak value difference. And that's a low frequency, because this figure shows that you can see in the experiments, due to the wind effects, they are quite obvious low frequency motion characters of the whole system. But this cannot be obtained very well by the numerical analysis. This problem told us that the low frequency motion estimation might not right if we only have the numerical analysis. And many other scholars, especially Unreal and Mary in Netherlands, they also found this problem. So in the OC4 project, their conclusion also emphasize that the low estimation of the underestimation of the low frequency motion. It could be a risk for the offshore industry, offshore wind industry, if you don't take any experiments, if you only rely on the numerical analysis. there could be a risk. And this risk can lead to not only the risk of the wind turbine, but also the risk of the mooring system and also the cable. The cable connected to the offshore wind turbine. And this risk brings to the next method of artificial intelligence technology. So with the theoretical analysis and the auto test experiment, traditionally for the traditional offshore industry, these two methods worked very well to have people to understand the dynamic performance of the offshore engineering structure. But for floating wind turbine, personal view, they are not sufficient, because neither method can provide a most accurate very well. So people think of some other technology that can be used, to give a better estimation and to give a more comprehensive simulation results. Then we are thinking of AI technology. So AI, artificial intelligence, it's very promising nowadays. And so we use this method, aims to combine, or we aim to take advantage of the numerical analysis and basic experiment, both methods together with the AI technology. And then we want to reach a method can be used to predict the dynamic performance of the floating wind turbine in a more accurate and a more easily way. In addition, if some owner of the floating wind turbine kindly can provide some full-scale data, it'd be much, much better, because full-scale data can give us the most accurate way. So during the past 5 years, I'm leading my team at Newcastle University. We conducted a lot of research on how to use AI technology with numerical analysis and basic experiment methods to reach this aim. So let's think about 3 years ago, we proposed a method. The name is called SADA. The long name is called Software in the Loop Combined Artificial Intelligence Method for Dynamic Response Analysis of Floating wind turbines. So we simplified this name as SADA. So this method is not, personally, I think this is not only a method, it's a concept. It's a very new concept. Some people call it PINN as a physics-induced neural network. Similar way in AI technology. But we think that the SADA is very useful and I think feasible in the floating wind turbine field. This method uses concepts of the software in the loop, not hardware in the loop, but software. And it uses AI for the floating wind turbine analysis. In SADA, there are three fundamentals. Each of them all of them are important. The first fundamental is an in-house program, that is Darwin, the theoretical program. You must have it. And normally, it's very difficult for you to use for people to use this method only with commercial software, because commercial software is blocked. You can use it, but you cannot get access to the code in themselves. But in SADA, we must use the code. So we need a Darwin, similarly in-house program. So this is the first fundamentals. The second one is machine learning or use AI technology. And I think AI method is updating every day. Many scholars in the world, they are developing their AI technology and they publish online and let other people to practice, to test it, and finally to confirm that which one is better, the best. So we can use those research outcomes easily using through the latest AI method. And the third fundamental is KDP, is key disciplinary parameters. I call it KD. I think that KDP is very, very important in using SADA. Why? Because KDP, although from its name, because its name is just parameters, but they are not only the parameters, they are also an interface between the date, between the big date and the program, the Darwin program. It's a new interface. And KDP is also the supporter of the neurons. We put neurons in Darwin to make it smart. And KDPs are the supporter where the neurons are placed. So the structure of SADA is shown in the figure. I can introduce the fundamental structure. In the middle part of this structure is Darwin. So you must have a program, in-house program, developed by yourself. You know which KDPs, which parameters are important in the system. There are thousands of parameters in your program, but only maybe hundreds, 100 or 200 are most important. When you choose them as a KDP, then you put neural networks in this KDPs. As on the right side, the AI to apply the AI technology, you place those neurons in the KDPs. You can deploy different levels. Currently, we deploy only one level to simulate the mean value of the dynamic performance results. And we are going to employ the second level to achieve the standard deviation, or the third level, fourth level to simulate the skewness and kurtosis. And on the left, you can see there's a date where we can obtain the date. We can obtain the date from basic experiments, or we can obtain the date from the full-scale measurements. We use this date and the neural network to do the AI training. So the training can last a longer time, but after training, the Darwin, the in-house program, will be trained to be smart, to be very smart, and it can be used specifically for the reference floating wind turbine. So this is the structure, whole structure of the SADA method. So as what I explained, KDP, very important. So which parameters can be used as KDP? It's rely very well on the people's experience. That means that the people who develop the in-house program, that people know which parameters are important and more sensitive and more efficiently that can be used to do in the whole analysis. And in addition, the people know how to define the boundary value for these KDPs. This means that the KDP can change from the assumed value, but it cannot change and freely. So it must can only change within a reasonable boundary. And how to define the boundaries is rely on the people's experience. Here are some examples of the KDPs. In aerodynamic load and hydro, you can see that for some coefficients, especially the added mass and the damping coefficients, that in the past, people assume that there are some fixed value for these parameters. But in SADA, they can change. They can be optimized, but within a reasonable boundary. So next, I will give two examples for the validation of SADA. The first one is that the basic experiments I just introduced, using that the experiment date that obtained from deep water offshore basin. So you can see that there's some environmental parameters, and we choose the KDP. We select 11 KDPs totally. So you can see the different parameters, but they're very simple, just 11. And we choose 4 testing cases. They are all irregular wave testing cases. We use the first 3 as to provide the date for the data training, AI training. And we use the last one, case 4, for comparison and to validate whether the SADA can provide a good AI training result. The training process is very complicated, and I don't want to say too much in detail, but I would like to use this figure on the right, if you can see my mouse here. For some easily comparison results, this is for surge motion. That's quite important for the high wind turbine. During the comparison, when compared with the last one, you can see the black line, they are the testing results. And the red lines, they are the Darwin calculation without AI training. It means the pure theoretical analysis. So you can see there's some difference between the black lines and the red lines. So after AI training, we have the blue lines. So at least you can see that blue lines match much better with the black lines than that of the red line. So this proves that using the SADA method, we can make the in-house program Darwin much smart and much useful to predict a better simulation result. So this is the first case of study. And I want to also introduce another one, the second one. It's about, this is it's a full-scale data result. This is a high wind in Scotland. I think under most consideration, all the full-scale dates are confidential. That means the owner don't want to share the full-scale dates with academics. This is also one of the problems that we often complain about the owners of the offshore wind industry. But fortunately, that the Equinor, who owns the supporting system of the high wind platform, the high wind turbine, they kindly provide in total 10 cases dates with catapult at Newcastle, UK. They share 10 cases dates with catapult, and the catapult work very well with us. So we obtain these dates to practice that whether that SADA can work well with the full-scale dates.
Professor, sorry for the interruption. We will have 15 minutes left for the presentation time. Just a reminder that, okay,
no problem.
You may continue.
Yeah, yes, okay. I finished, I think, around 10:30. Okay, and after we have the case of study date, we check the dates. We found the dates are not very well, but can be used. The challenge is that we don't have heave motion. Here we don't have heave motion, and we don't have the data of the wind turbine. So this big problem. So we have to make some simplification, and so we use the 5 megawatts, the published 5 megawatt wind turbine, replacing the real one on board. This is 6 megawatts GE wind turbine, but GE didn't want to share anything about their data. So we have to use the published one, 5 MB, to replace that. So this is, I think, a very broad assumption, but we just use it to try to see whether SADA can do it better, even under a very difficult situation. And this time, we choose many KDPs, more than 11 in the first case of study. We choose 2 sets. The first one is 51, and second one is 108. We choose many KDBs, and it means we deploy many more neurons in the system. And these are results. I still want to use the figure to show the results. You can see that, if you can see my mouse. For this one, this is the errors comparison. So if without AI training, the percentage of the errors can reach more than 50%. It means that's very not good. But with 51 KDPs AI training, the errors can reduce sometimes to 30%. And with 108 KDP AI training, you can see the errors reduced around 10 to 20%. This means that with more AI training, the simulation results become more accurate. And this figure also on the right also show this tendency. The black line is a measurement, the full-scale measurement. So without AI training, it's a red dot line. You can see no matter this STD and the mean, they deviate quite a lot. So with 51, it's a blue dot line. It's better, becomes better. And with 108 KDP, the green line, you can see the tendency and the variations becomes closer to that of the target black line. So this proves that even under very difficult situation, we don't have the wind turbine dates. SADA can still simulate, can still bring us relative, much better simulation results for the system. So this means that it is very smart. It's smart. So finally, conclusion. Conclusions are very simple. Floating offshore wind turbine as a promising future of the world. But there are still many challenges for the application, especially safely and in an economic way. This means that how people can reduce the cost of design, installation, manufacture, operation, and maintenance. But how to achieve these goals, that we must obtain a method. We must have a method that can accurately predict the dynamic performance of the floating wind turbine in complex sea states. This is still a big challenge in face of the offshore wind industry. The many methods, numerical analysis method, Bayesian experiments, and also CFD. I didn't mention CFD today, but it is a method. And artificial intelligence technology is a promising way. It provides a possibility to overcome this challenge. But I must say that using AI technology in SADA method, we must build a solid theoretical foundation of the floating wind turbine. We cannot neglect these theories, those theoretical methods, and only rely on AI. If some people only want to use AI and to save time on the theoretical analysis, I don't think it's probably, at least at this moment, it is not possible. We must build a solid fundamental basis. We must understand that the aerodynamics, hydrodynamics, and the code, we must have our in-house program code that we can use the artificial intelligence very well to help us to understand the technology, I understand the dynamic performance of the floating wind turbine very well. Okay, that's all for my presentation. Thank you very much, and I'm very glad to answer your question.
Thank you very much, Professor Hu, for the very insightful lecture materials about offshore wind farm structural analysis using AI, which I'm sure inspires future engineers from Ocean Engineering ITS for open doors in the future, which is very much appreciated. And for this Q&A session, it will be limited for 15 minutes long, and each participant have no limitation to ask as long as it is linear to our lecture materials. And to begin our Q&A session, participants may use the raise hand feature, and once the participants' names have been mentioned, you may start to ask your questions directly and start a two-way discussions with the professor. And for the participants who still have trouble with their own devices, please send your questions through the chat box or private message me, and I will read it to Professor Hu. And please be noted that participants who raise their hands will be prioritized over those who ask in the chat box. So, Professor, you may answer the participants right after the question is given. And now the Q&A sessions may begin. Are there any questions on the floor?
Yes, I also think that to type your question in the chat bar is very good way. Yeah, okay. I see someone raised hands. Yes, please.
Mas Aldin, you may ask your question right away.
Okay, thank you, Shafiq. Thank you for the great lecture today, Mr. Wu. Actually, I'm very interested in this kind of topics because I also studied about the numerical analysis of floating offshore wind turbine and also the implementation of the offshore wind turbine in Indonesia. For your information, there is no offshore wind turbine yet in Indonesia. So yeah, I am very curious about these topics. Actually, I have two questions. The first question is about the servodynamics. From what I know about servodynamics is like a control system of a wind turbine. Is that kind of control system also implemented in the experimental studies? That's my first question. And my second question is, in a practical point of view, what are the design codes or design criteria that are used, especially in UK?
Okay, thank you for your question. About the first question, it's about the control. Yes, control is used in the offshore wind turbine. For example, the pitch control and to help that the wind turbine to maintain a stable power expectation. In the experiment, control can be simulated. But when at the time in 2014, when I conduct experiments, that technology is not mature. So I didn't use control in my experiments. But I know that currently in some other basin, for them also in the team at the deep water offshore basin at Shanghai Jiaotong University, that team has mastered the skill at how to simulate the control in the experiment. And it means that the blade of the pitch angle of the blades can be simulated accordingly during experiment when the wind speed changes at the blades and pitch angle can be adjusted accordingly. It requires quite a lot of the, I think, mechanical engineering technology. I mean, to manufacture some detail and facility, I think, equipment or devices on board, because the mass problem is a big challenge. You can't manufacture very heavy, very complicated structure in experiment facility because it's the mass control. So what I can tell you is that this obstacle has been overcome, and some other can do it. But unfortunately, that in Newcastle University, we don't have that kind of deep water offshore basin. So I myself my team doesn't have that kind of skill right now. But if you want to know more, I think I can introduce you to someone that's in the deepwater offshore basin at Shanghai Jiao University. They can let you know the latest research, or at least some journal paper published that you can refer to. Okay, and your second question is about the current offshore wind turbine. So sorry, I forgot that. What's your second question?
Yeah, my second question is the design codes or design criteria that are used.
Design codes.
Yeah.
In commercial, in the offshore wind industry, in UK, people use some bladed Hawk 2. You can HAWC2. Yeah, Hawk 2. Hawk 2, I think, is a DTU in Denmark. Siemens code. Siemens use this code very well. There's also, I think, open. If you know it, open fast. That's an open code. Yeah, has also been used very well in academic field. Yes, open Unreal public that's open fast, so you can download freely for free use. So and beside this code, there's also another one called Ocaflex. That's a UK company code. Ocaflex can be used to calculate the dynamic performance. But in my personal view, I do think OpenFast and Hawk 2 are the real, I think, dynamic performance analysis tool, because they are time domain analysis tool and can consider the aerodynamics and hydrodynamics at the same time. My in-house program, Darwin, is not open code. It's just in-house program. You can we look on it as a mini, in a small open fast, and this code can also be used to conduct research. So I recommend you use OpenFast. It's published and easy to get access. Okay, that's my answer.
Okay, thank you very much, Mr. Hu.
Yeah.
Thank you very much for your answer.
Thank you very much, Ms. Aldin, for the question, and Professor Hu for the answers. Participants, we still have time for a few more questions. So once again, are there any other questions on the floor? You may raise your hand.
Oh, you can type in the chat.
Or you can type in the chat, exactly.
Yeah. I think that's during the past 3 years, during the COVID, I also made some online lecture, and people like to use the chat to ask questions. They're very, very convenient for you.
It is, certainly, Professor.
Yes.
Someone has private messaged me, Professor, permission to ask. The presentation earlier discussed the hybrid rigid flexible multi-body system model. I have read several journals on offshore wind turbines, which are similar to what Professor Hu mentioned. But the uniqueness is that there are several journals that integrate offshore wind turbines with aquaculture. So they use a wind turbine to power a semi-automatic aquaculture. What is Professor Hu's response, and what are the possible expansions to it? Is it possible to commercialize? And what do you think about it? Thank you very much.
Oh, yes. I know this is one of the application. Yes, for the floating wind turbine, for wind turbine to support the agriculture. But currently, there's only some small scale application, which means that wind turbine is not larger one. But it's possible that in the future, if the agriculture can be very large agricultural structures, and can be large enough to support the offshore wind turbines. And yes, I think it's possible. It is possible to install the offshore wind turbine on board. But there's a big challenge on the structure design for the agricultural structure, because offshore wind turbine will bring a large aerodynamic load to the whole system, this might induce some additional motions and dynamic responses on the whole system. So this must be considered carefully because it could induce some additional fatigue load on the agricultural structure. Wind has some obvious low frequency motion characters. This could be can transfer, the wind turbine can transfer this low motion characters to the agricultural structure. So currently, most agricultural structures are very, we can see they are not robust. It's a weak structure because that only supports the fish to live inside. So it does not has a requirement for very strong structure. But if supports a wind turbine, it could have to bear some additional wind-induced load on the structure. That could increase the cost for the whole system. And so it's trade-off, it's a balance between economic and safety. So for my personal view, I think if in the future the agricultural structure can be built very large, can provide a lot more buoyancy and a strong structure, then it is possible to support floating wind turbine on board. So that is my answer.
I see. Thank you very much, Professor, for the answer. Participants, it seems that we still have a room for one more question. So are there any questions on the floor? You may raise your hand or type in Zoom chat. Calling once, calling twice. There is a chat. There is a personal chat to me. But we will accommodate the any other speakers who wish to relay their questions on mic by raising their hands. Okay, calling again before I open this question from the chat. Calling once, calling twice. Okay. Okay, so for the question from the chat. So, Professor, we know that there are both aerodynamic and hydrodynamic loads in offshore wind farms. And in general, the aerodynamic loads are the sort of loads that we try to convert to energy with the turbine. However, is it possible that we try to harness the hydrodynamic load as well? Will it be efficient, or will it be dangerous to the operation of the wind turbines themselves? And are there any other way to fully harness the full load faced by offshore wind turbines other than the spinning blades? Thank you very much.
Yes, I think that there are some previous study on combined hydro, I think wave energy converter and wind turbine together. There's some applications and even some full-scale testing on this possibility. Wind turbine is no problem. It's work well. The challenge is wave energy converter. Because the cost of wave energy converter is quite high, much higher than that of the wind turbine. So that's why the reason why it has not been commercialized yet. And this is one of the challenges. The other is that the wave energy converter is put in water. So the marine growth is another big challenge. Marine growth that can change the hull shape greatly, especially in the sea water is warm. I think in cold water it's fine, but in warm water, it's marine grows quickly. So this might be a big challenge for Indonesia academic if you want to harvest wave energy converters. There must be some I think edge-cutting or cutting-edge technology in the future developed. I know that in Indonesia, because it's near equator, the wind is small. But now, I think the wind turbine becomes larger. This means it's possible that you can harvest wind energy from the higher latitudes. Because although the near sea surface, the wind small but higher, for example, the 200 meters higher, the wind is still strong. Now people are developing 25 megawatts. wind turbine, which its height could be reached 300 meter, 400 meter. So where the wind resource is still abundant. So this is one of the, I think, possibility in the future that for the countries near equator can also harvest wind energy in the future. But now, if it's small, for small wind turbine, it's not economic feasible to be used. But wave energy or some current, tidal energy is possible. And especially, I think I know that this oceans in Indonesia is very deep, so maybe there could be some another, I think, energy from oceans called, I think, temperature difference. If you use temperature difference, it's also a big resource for energy harvest, but it's relied a lot on the experience of the offshore engineering. So also a lot of investment. Well, anyway, for people that we want to harvest renewable energy from ocean, there are many ways, not only wind, but also many other ways. So it's also the very important, I think, field that can be collaborated in the future. Thank you.
Very insightful, Professor. Thank you very much for your answers. And unfortunately, due to the limited time, due to time constraints, it seems that I have to hereby close the Q&A session and discussion session for now. However, I would like to appreciate for the abundant transfer of knowledge, first of all, from Professor Hu and enthusiasm from the participants from our guest lecture. I hope that we have found a new inspiration towards maybe some of us are looking forward to write our final thesis. And from Professor Hu's guest lecture, we are inspired to explore further regarding the offshore wind turbine, especially regarding the potential 25 megawatts of very, very large energy potential wind farms to be built in Indonesia later in the future. And lastly, it is very much an honor, Professor Hu, to be the moderator and assist your presentation for today. My name is Shafiq, and wassalamualaikum warahmatullahi wabarakatuh. To Advira, the stage is yours.
Okay, thank you so much, Shafiq. Wow, I must say that that was a really insightful session. And by this, I would like to express my gratitude to Prof. Zhiqiang for his expertise and insights. They were invaluable in helping us understanding offshore wind turbine numerical analysis and AI integration. And in addition, I would also like to express my gratitude to today's brilliant moderator, Shafiq, for guiding us through today's guest lecture. We truly appreciate the time and effort you've put into preparing for this webinar and for engaging with our audience. And as a token of our appreciation, we would like to present Professor Zhiqiang with a certificate of recognition. The certificate acknowledges the dedication and commitment in sharing his knowledge and expertise with our audience and serves as a reminder of his valuable contribution to this webinar. And before moving on, we'd like to document this beautiful session. So to Professor Hu, you may face directly to the camera and on my count. Okay, so in 3, 2, 1. Okay, once again, 3, 2, 1. Thank you so much, Professor Hu. And we will send the certificate to you by email within the next few days. And if you do not receive it, or if you have any other questions, please feel free to contact us. And as we are near to the end of our session, I would like to take a group photo of all of our attendees. And to make this happen, we kindly ask that you turn on your cameras for a brief moment. And it will only take a few seconds to capture the photo, and it will be great to have a visual record of this wonderful event. So if you are comfortable in doing so, please turn on your cameras now, and we will let you know when the photo is being taken. Okay, everyone, I'm really looking forward into seeing your smiles on the screen. So if you don't mind, please turn on the camera. Okay, we will still be waiting for a very few brief moments before taking a photo. Okay, so perhaps we'll start for now. I'm counting by 3, 2, 1. Okay, once again, in 3, 2, 1. Thank you everyone for your participation in the documentation session. And ladies and gentlemen, we have now come to the end of today's webinar. And before closing this event, we encourage participants to fill in your feedback through the QR code on the screen or through the following link. Okay, you may now see it on the screen. Thank you everyone for your participation, and we would like to take a moment to express our gratitude once again to each and every one of you who participated in this webinar today. Your active engagement and thoughtful questions have contributed to making this a successful event. We appreciate your time and interest in our topic, and we hope that you have found this webinar to be a worthwhile experience. We would also like to thank our speaker, Professor Zhiqiang, for his expertise and willingness to share his knowledge with us today here. And we appreciate his dedication and commitment in making this event a success. We hope to see you in our future event. And that is all from me. Take care and goodbye. Wassalamualaikum warahmatullahi wabarakatuh. Thank you, Professor.
Prof. For
Thank you.
your
Thank you. Bye-bye.
Bye.
Have a great day.
You too.
Have a
Bye-bye.
good day. Terima kasih Mbak Advira, Bapak Ibu sekalian yang hadir. Saya lihat di sini tadi ada Prof Mustain, ada Pak Dendi, Bu Santi juga ada, dan beberapa alumni juga. Terima kasih banyak atas antusiasmenya. Tentunya ini semoga bermanfaat untuk semuanya ya. Dan kerjasama dengan Prof ini harapan kita bisa kedepannya bisa lebih banyak lagi, juga tidak hanya dengan Prof ya, tapi Newcastle University secara umum. Jadi silahkan nanti kalau mahasiswa tertarik untuk mengadakan kegiatan ataupun misalnya ingin kolaborasi dalam bentuk yang lainnya, silahkan gitu ya. Terima kasih banyak untuk teman-teman panitia dari HIMATEKLA juga. Saya undur diri ya. Terima kasih banyak.
Terima kasih Bu Sade.
Sama-sama, sayang. Terima kasih.
Terima kasih Bu.
Terima kasih Bu. Selamat sore.
Selamat sore. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.